The most important interpretation of quantum mechanics in the first half of last century has been the Copenhagen interpretation. James Hopwood Jeans, an English physicist who backed idealism, said of quantum mechanics, "I incline to the idealistic theory that consciousness is fundamental and the material universe is derivative from consciousness, not consciousness from the material universe. In general, the universe seems to me to be nearer to a great thought than to a great machine. What remains is in any case very different from the full-blooded matter and the forbidding materialism of the Victorian scientist. His objective in material universe is proved to consist of little more than constructs of our own mind. To this extent, then, modern physics has moved in the direction of philosophic idealism. Addressing the British Association for the Advancement of Science in 1934. That was 7 years after Niels Bohr and Werner Heisenberg had completed the Copenhagen interpretation. Niels Bohr and Werner Heisenberg both had important contributions in field of quantum mechanics and in general nature of reality. What was in Copenhagen interpretation that opened the door for scientific idealism? Copenhagen interpretation is a set of several principles which serve together as an explanation of quantum mechanical phenomena. Under Copenhagen interpretation, a smoothly evolving wave function, as developed by Erwin Schrödinger, represented the state of system in its entirety before observation. Such a function was, however, probabilistic and not definite, and thus incorporated Heisenberg uncertainty principle. However, when any observation was made, by some means, the wave function collapsed to a definite value. The probabilistic quantum quantity converting into definite classical value explained the wave-particle duality that Bohr believed existed inherently in the world. However, to still explain how the aggregations of quantum particles stood justified in light of theorems of classical physics to a great extent, Copenhagen interpretation argued that statistically the quantum particles are describable by classical physics. There are few things that follow out of quantum mechanical experiments and attempts at their explanation. For example, quantum mechanical arguments show that effectively all particles extend essentially to infinity. This is due to the fact that there is no theoretical upper bound in error in perceiving the position of particle. The bounds of Schrödinger equations also extend to infinity in all directions, even though the probability of all potential positions is not uniform. This is very important for several reasons. For if wave-particle duality indeed is an inherent part of the ontology of the world, it follows that particles exist as a wave circumscribing whole of the universe, even if potentially. This also raises an interesting thought experiment, which is verified by actual experiments. For example, in 1927 by German physicist Friedrich Hund, the theory behind Heisenberg's uncertainty principle holds, and indeed nature of particles in wave form is probabilistic, then we would find that there is a small probability to expect quantum particles to be at positions that is not possible according to normal physical laws. Assume a quantum particle in a box, or well restricted in the space by walls, which prevent quantum particles from jumping through it unless they possess enough energy. In a normal scenario, we would never see such a particle crossing the barrier and reaching the other side unless additional energy is supplied to the particle. However, if nature of position of a particle is probabilistic, and what creates Heisenberg's uncertainty is indeed ontological, then there is a small chance that the particle would be found on the other side of the barrier. If the barrier is very thin, such probability is large enough to be observable in actual experiments. It is interesting how the concept works very similar to video games, where sometimes an in-game entity with high speed can pass through barriers through glitches. If the entity really travels, it is impossible for it to pass through in-game walls without such walls getting destroyed. However, what happens in a game actually is that what is shown on a screen is just representation of a mathematical function. The sprites de-instantiate when the function calculates their new position and then re-instantiates them on screen, and hence they can pass through a wall without any problem. If the speed of an object is so high that during the next check by the algorithm it would be beyond the barrier, it is reinstantiated on the other side. As the discussion depends ultimately on wave-particle duality, it is important to understand it. If a particle is passed through a double slit, it would form a pattern of discrete bands on the screen, according to classical understanding. However, a quantum particle, according to wave understanding, would form an interference pattern on the screen, as it is not located at a single location at a particular moment in time, and that is observed in experiments. However, if a detector is added to the experimental setup, which detects through which slit the particle passes, a discrete pattern of bands is observed. This led to the development of quantum eraser experiment. If after a detector is added, an eraser is also added, which again makes it impossible to know through which slit the particle passes, a continuous interference pattern is observed again. This shows that the knowledge of the path taken by the quantum particle is what is causing the particle to behave as a particle instead of wave, as the knowledge restricts the choices that the particle has. However, in all of these experiments, particles touch the screen after their position is measured or erased. What if the particle is allowed to touch the screen before the which way information is measured? The delayed quantum choice eraser experiment does just that. It adds a layer to the setup such that the which way information is obtained after the particle has already struck the screen. Hence, it is assumed that the measurement would not affect the pattern found on the screen. However, that is not what is observed. If the which way information is detected even after the particle strikes the screen, the discrete pattern is observed, while if such an information is erased again after the particle has already struck the screen still shows a continuous interference band. There is a strange retrocausality looming here. Not only our knowledge collapses the wave into a particle, it can cause such a collapse even after the incident has already occurred, as long as it has not been recorded. The primacy of knowledge, while fueling idealism, is not itself evidenced by Copenhagen interpretation in a direct way. Copenhagen interpretation does not argue that wave function represents anything ontologically true, but only a mathematical construction, and what is collapse is not really agreed upon, in the spirit of modesty and conservatism. But then what the wave function is, and what is collapse? Anti-realism, as proposed by some form of idealistic theories, was too much of a burden to be borne at that time. Yet many philosophers bordered on views close to it. Bohr was at least a transcendental idealist. Wigner believed that consciousness collapsed the wave function. Pauli believed that mind and matter were complementary, and Heisenberg was almost an idealist. However, any dominance of idealism that existed in academia was soon challenged by G. E. Moore and Bertrand Russell. G. E. Moore, who was a student of F. H. Bradley, a famous British idealist, but later became a staunch anti-idealist, gave an argument against idealism which became famous. G. E. Moore's argument was, here is one hand, and here is another. There are at least two external objects in the world. Therefore, an external world exists. This argument, while obviously employing an element of mockery and dismissal, follows from what G. E. Moore believed to be the common sense refutation, a defense of common sense. Yet G. E. Moore's argument can be converted into a formal argument under more charitable interpretations and could be stated as, there are a lot of things we accept as true by common sense, like reality of external world, which can be known from our parlance. Any argument in favor of idealism would be less obvious than acceptance of those things as true. Thus idealism has insurmountable burden to bear to prove its case against common sense. Hence, idealism is never justifiable. However, Ludwig Joseph Wittgenstein, an Austrian-British philosopher, argued that such arguments are problematic. Wittgenstein tried to show that the problem with commonsensical arguments is that they often do not mean what is evident from their wording. One of the arguments that can be developed from Wittgenstein's view to critique commonsensical arguments against idealism is as follows. The parlance used by humans while referring to facts is either because it shows true belief of them or it is a matter of convenience. If it is not a matter of convenience and really represents true belief of people, then making it more verbose but academically sounder would not make it less believable. Reality of external world, if made more verbose but academically sounder, would make it less believable. Hence, the parlance used by humans while referring to reality of external world is out of convenience. In fact, because statements regarding reality of external world, as they are made sounder, become less believable, hence common sense dictates against reality of external world. Hence, even a simple statement like, "Here is one hand," is riddled with complex assumptions that become evident when the argument is made more modest and academically better, which should not be the case if the argument was from the start entirely believable. Making an argument more modest and more academic should increase its believability unless it is believed because of emotions. A better statement that reflects most beliefs of commonsensical belief is that "I know there is one hand." But that statement again raises the question of what constitutes knowledge, a basic question philosophers have been trying to answer since several millennia. Hence, the argument already begs the question in favor of ontological realism by begging the question in favor of epistemic realism. Idealism fell quickly because the way realists framed the discussion, it was very intuitive to accept realism, especially as naturalism also began extending its influence. A little bit of idealism that was still alive was being constantly mixed with several other narratives, which culminated into sort of New Age beliefs that quickly became target of attack for rationalists and empiricists. Skepticism, as promulgated by Kant and Wittgenstein, became replaced by the modern skepticism, which became a tool by naturalists, empiricists, rationalists, and atheists to justify what they presumed to be scientific and commonsensical beliefs, a reversal from what skepticism originally meant. However, materialism failed to offer basic explanations for quantum mechanical phenomena, especially because after boasting of its complete dominance during reign of classical mechanics, the doctrines of the system needed overhaul in light of new conclusions of science, which very few materialistic philosophers were able to provide. In fact, materialistic ideas were attacked, perhaps most significantly through quantum mechanics, through what is known as von Neumann-Wigner interpretation, an interpretation of quantum mechanics which argues that it is the consciousness which has the specific privilege of being able to collapse wave functions. The determinism of materialistic theories was partially rescued by Bohmian mechanics, an interpretation developed through the works of Louis de Broglie and David Joseph Bohm. Bohmian mechanics argues that along with the wave function as governed by Schrodinger's equation, there exists a guiding function which stores the initial position of all particles in the universe. Hence, the uncertainty in Heisenberg's uncertainty principle is not a real feature of the world. The variables dictating future position and velocity of particles are, however, hidden and non-local, and thus cannot be measured directly. This guiding function, along with Schrodinger's wave function, determines the exact position of particles in future. A measurement makes the conditional wave function settle to a value, which is known as collapse. However, Bohmian mechanics suffers from a lot of problems. The Cauchy-Specker theorem offers a strong argument against presence of non-local hidden variables. However, there are other criticisms of Bohmian mechanics that are far easier to understand. Bohmian mechanics holds that there is just one single wave function for the whole reality. It is often argued to be like a field which permeates the whole universe. But what is not known is whether it is just a mathematical construct or is it really real, and what explains the behavior of wave function if it really exists. How does the wave function carry information of the whole universe? In what form it stores it? Because no longer one can hold, under Bohmian mechanics specifically, that the wave nature of particles is a feature of individual particles, for then there would be no wave function of universe. Bohmian mechanics also cannot explain what causes collapse, but more importantly, why is collapse only caused when measurements are recorded, but not when measurements are made without being recorded. Clearly, whether the measurements are being recorded or not should have no impact on reality, because the interaction between what is being measured and what is measuring it is not contingent on whether the measurement is being recorded. These problems with Bohmian mechanics make other possible interpretations of quantum mechanical data seem more acceptable. Many worlds interpretation is one such interpretation. Hugh Everett III, an American physicist, tried to address the problems posed by quantum mechanics by arguing that each measurement split the world into different worlds. Hence, while the wave function was probabilistic, every possibility was necessary to occur in some world. This theory, which was dismissed at the time and gained serious recognition only after Everett's death, had strange consequences. All possibilities occurred. This means that there was some world in which a human never died. A strange view that appears to be a great foundation for some serious science fiction. This led even Everett to believe that he would never die. In some universe, he was, along with all other living beings, technically immortal. Everett asked his family to dispose of his remains in a trash, presumably because of his atheism. His daughter Elizabeth wrote before committing suicide, "Please sprinkle me in water or the garbage. Maybe that way I will end up in the correct parallel universe with Daddy." Many worlds interpretation, however, is also not free of problems. If universe splits into many different universes, from where such energy to create so many other universes comes? Where does all the matter comes from? Of course, one has to deny reality of energy to believe in such a view. The second issue with the view is that if every probability is instantiated, does the number of universes the universe splits into is determined by fraction in which such a probability can be expressed? What if such probability is irrational? Of course, probability for many events could be fractional multiple of some irrational number like pi. What happens then? Is it approximated? To how many digits? And what decides which universe has a particular instantiation of a probable outcome? Or does that not matter because all such universes are equivalent in some sense, even though their contents are different? This is the crazy problem of quantum mechanics.